Hi, everyone. Thank you for joining us today for the OTDR Setup and Analysis webinar, co-hosted by TRS-RenTelco and EXFO. My name is Lindsay Wells. I'm the marketing manager at TRS-RenTelco, as well as the moderator for today's event. A few housekeeping items before we begin. This webinar is being recorded. We will email the presentation slides, as well as a link to the video recording to all registrants later this week. Feel free to submit questions throughout the webinar using the QA section of your control panel located at the bottom of your screen. Our speakers will address questions during the presentation as time permits. For those of you just joining, today's webinar will cover OTDR Setup and Analysis. EXFO Applications Engineer Kevin Perez will demonstrate how to optimize OTDR settings to avoid and overcome common issues related to misconfiguration, bad cables, and dirty connectors. But before we turn things over to Kevin, I'd like to introduce Scott Wrinkle from TRS-RenTelco. Scott is a regional sales director for TRS, managing the Western U.S., Taiwan, and Southeast Asia territories. He has worked in the test and measurement industry for 25 years and is an expert at helping customers create operational efficiencies, measurement equipment through less traditional methods, such as rental and leasing programs. We know there are a lot of demands on your time, and we appreciate you joining us. I'll now turn the presentation over to Scott.
Hi, everyone. My name is Scott Wrinkle. Thank you for joining us today. We work with many folks on the line today, helping to provide short-term equipment needs, as well as if you have any types of financial issues, you don't have the budget, or you don't have the approvals ready to get the equipment. Our goal is to get you equipment immediately. Everything at TRS is designed to get you answers and equipment quickly and accurately. We have a large facility based in Dallas, Texas, right on the DFW airport. We have a lot of our own programs. We do a lot of our own calibration. And with the EXFO equipment we'll be talking about today, we're actually able to, again, get the equipment. Our goal is to get the equipment to you tomorrow if you need it, as well as provide you with quick exchanges and making sure that you're up and running. We do a lot of our own calibration internally. You can see on the slide here, that is a picture of the TRS-RenTelco calibration lab. We do run shifts around the clock. And our goal is to get you equipment you call in today. We can get it out today and get it to you tomorrow, having next day delivery available. We're very proud of our customer service. We're the only company in North America that offers 24/7, 365 customer service where you can call up and actually talk to a live person. That means when you're a technician or your technician teams are out in the field and having troubles, they can give us a call and we can work at that moment to fix the situation. The other option is they would have to come in the next day, talk to maybe a planner or a buyer, translate the problem, and then have them work through it. And again, what we can do is start processing that exchange immediately. We're very proud of our customer service record. And again, we really want to focus on test and measurement with equipment. For represent Kevin Perez. Kevin has been in the telecom industry for 29, starting with excavation as a laborer. Kevin traded in his shovel and backhoe laying cable across the U.S. He later worked for a Tier 1 service provider as a splicer and tester, working on installs and disaster recovery. Kevin became an operations technician, turning up and maintaining DS1 and 10G systems, leveraging his field experience. Kevin delivers a unique perspective, which shows in his educational approach when delivering expert content. I am very pleased to introduce today's presenter, Kevin Perez.
Thank you very much, Scott. As Scott mentioned, my name is Kevin Perez. I am a senior applications engineer with EXFO. And so today we will be covering OTDRs. It's something that's very near and dear to my heart. I was a tester for quite a while. I placed fiber and pulled a lot of fiber, and spliced and tested a lot of fiber. And so a lot of my training style is kind of revolved around that. So, one of the biggest issues that I'm seeing in the industry today, so I analyze tens of thousands of traces every month for our customers. And, quite frankly, one of the biggest issues that we run into is, getting results right the first time. That's such a huge issue that we have in the industry across the board. And so that's one of the things that we'll be talking about today, looking at the OTDR setup, from a very high level, and then getting in there and analyzing the trace to make sure that what we have in front of us is relevant, because nobody wants another truck roll, right? As we get up into higher and higher count fibers, on a daily basis, I'm looking at 864s and 1728 fibers. So these are very, very high count fibers that, quite frankly, it takes a lot of time to test them, honestly. And we want to make sure that we do it right the first time. So that's kind of the goal of this here today. And so if anybody's ever sat into my training, and I do quite a few of these, so there's a good chance some of you might have, I always start with a little bit of a fiber refresher. This one's going to be a little bit more truncated. It's going to, it's not going to be as detailed, because I really want to get into the analysis portion of it to make sure that we do first time right testing. But to get to that point, it is important to talk a little bit about fiber and a little bit about OTDR theory. So how OTDRs work, because when we start analyzing the data, this is what we're looking at, right? And this is the kind of information that we're looking at. And so, so with that said, I kind of have just like a little bit of a whiteboard up here. And so this whiteboard, I'll be drawing on, and I'll be, kind of showing you some of the things that I'm talking about. So when it comes to fiber, what are we talking about, right? So in this particular series, I'll be more focused on single mode fiber. And so single mode fibers, roughly 8 to 10 microns, are in that range, depending on the type of fiber that, that you're deploying. And so it's important to understand, that we are dealing with very, very small sizes of fibers. Human hairs, 40 to 100 microns, in that range. So we're talking about very, very small fiber. And there's two critical parameters that we're going to look at primarily when we start looking at the results. And one is going to be loss, or power. And the other is going to be ORL, or reflection, right? And so there's, we'll talk about the difference between the two, but these are the two critical parameters that we care about, loss and ORL. So when we start looking at the results, these are two things that we look at very closely. And what is power? So power, or loss, is power is basically the amount of power that comes out of your transmitter, right? Or you receive into your transmitter. It can be measured in watts, but here in the US, we typically see it as dBm, which is a conversion from watts, right? So there's an equation for that. But when we look at our systems today, right? So you have a transmitter on one end, and you have a receiver on the other, and you're going to have some sort of fiber or infrastructure between them, right? And so power is how much power comes out. So if I could have, say, +5 dBm coming out of my transmitter, and say -15 dBm arriving on the far end. So this is absolute power, right? This is what your power levels are. Loss is the difference between the two. And this is measured in dB, which is a relative measurement. So the difference between +5 and -15 is 10 dB of loss. So in this example, I'm showing a fiber span, but this is also relevant for connectors and splices and those types of things, right? And so when looking at that value, that's pretty simple. Power in, power out. It's not rocket science when it comes to loss or power. ORL reflection's a little bit different. This is the percentage of light that reflects back. ORL is span reflection. So the way I like to look at loss is I look at loss like water pressure. So PSI, right? You have a certain amount of pressure coming out, and the amount of pressure that you lose is the same. And somebody's doing math for me there, and they're absolutely right. It's 20 dB of loss on that scale that I did. And so I'm certainly not known for my math, but and so on that earlier screen I did 10 dB, but it's 20 dB. And so so when you're looking at these values, right, between loss and power, I look at it like it's water pressure. Where ORL, I look at it as noise. And I know, and I do a lot of training, transitioning technicians from a copper coax world, so say twisted pair or coax into fiber. And noise mitigation is a huge thing for that world. When it comes to fiber, one of the biggest things that introduces noise into a system, particularly an amplified system, is reflection. So when I look at ORL, I'm talking about span reflection, right? And so the total power inputted versus the percentage of light that's returned. And this contributes greatly to the quality of the signal. And so that's what ORL is. It's span reflection. And a typical value that we might see for this, it's a positive number, 27 to 32 dB is typically what we see in the range of acceptable values from most of the customers that I work with. Reflection, on the other hand, is individual reflection at specific locations. So when we're talking about that in a test world, that's what we mean, right? So a connector has reflection, and those values are negative values. So typically we see between neg 40 to neg 50 as an acceptable parameter for most of the customers that I work with, right? These are pass-fail parameters, not necessarily specifications. And so that's reflection, and reflection is a percentage of light that bounces back. So it's not, 1 + 1 = 2 like you have with loss or power, but more of a percentage of light that comes back. There's a logarithmic equation tied to it and all that fanciness, but we won't get that deep into it. And so these are the two things, the two critical parameters that we look at very closely when we are talking about fiber. So it is very, very important to understand these conceptually from a very high level. And so with that said, it's important to understand how light propagates down this fiber. So fiber is essentially just a glass conduit, right? And what we do is we inject light at a very specific angle, and it reflects off of the cladding. So the core itself is very small, and wrapped around that core is cladding, right? It's cladding, and that cladding protects the core, but it also helps keep the signal within the core. And one way I like to explain it is if you're standing on the side of a lake or a pond, and those of you that have seen my presentation have seen this very remedial drawing from me. But essentially what it is when you're looking down at this smooth surface of water, it turns into a mirror finish, and you can see the trees and the sky. So for a very small section of the lake or the pond, when you look down at it, it reflects, and then you can see again the sun and the trees and the sky. That is the angle, roughly the angle that we need to maintain something called total internal reflection. That's how we keep the light within the core, is that we hit that one spot, we hit that one spot here, and we maintain total internal reflection. If we were to, say, inject light at a steeper angle, and it came in, and it did not hit that total internal reflection, it would run along the surface of the cladding, or it would bleed out into the fiber. So because we basically changed the geometry of the glass, we changed the angle of the signal propagation. For example, if you pinch a fiber and put a VFL on it, one of the little red lights, you'll see it shine through the jacket. You've essentially broke total internal reflection, and you can start seeing that the colors shine through. And so this is from a very, very high level. I don't want to get much deeper than this. This is what we're looking at when we're talking about how light propagates down the fiber, and this will come make more sense when we look at the OTDR. Anywhere where there's a change in material type. So in this particular example, this is fiber, and this is fiber. Here in the middle is air. And this is a physical connection, and in this example, a UPC connector. So an ultra physical contact connector that has a flat cleave. So it has a right angle here. So it has a flat cleave, right? And so spec-wise, we see UPC connectors. Typically, we see them half a dB or better. Actually, typical is probably closer to 0.2, 0.3 dB in loss. And reflection-wise, we see neg 50 dB or better. Better would be neg 60, neg 70, neg 80. Those are better values. And so that's what we typically see for a UPC connector. For an APC connector, we're also seeing about the same amount of loss, roughly half a dB or better spec-wise. And reflection, though, is neg 60 dB, which is significantly better or higher. And it's typically higher. We're talking about neg 70s, neg 73, neg 74. APC connectors or angled physical contact have an 8-degree cleave, and as such, introduces less reflection or noise, so to speak. And so it's important to understand that there are different parameters and different expectations for different types of components in your system, right? Back when I was splicing, we had a different parameter for ribbon splices versus single splices. So APC connectors and UPC connectors, spec-wise, perform differently. And the reason behind that is really simple pool table physics. And I do dumb it down a lot because I am really going more for, trying to get the concept. So conceptually think, if you picture a UPC connector, so you got a blue boot connector in a UPC connector. So I have this UPC connector. It has a flat cleave on the fiber. What that means to me is the reflection is going to return at the same angle. So if I bounce a tennis ball off the floor in my office and it hits the wall, which is my flat cleave, it's going to come back roughly at the same angle. And what the problem with that is that the maintains total internal reflection, which we do not want. We don't want that reflection coming back because this is what causes issues with signal noise ratios. This is what causes dribbling errors. It increases the dead zone on an OTDR trace. It causes retiling, retransmissions. A lot of that stuff can be tied directly to reflection. How APCs are better is APC still has the same angle coming in, but now imagine my wall having an 8-degree angle on it. The reflection is going to return at a slightly different path, just enough to break total internal reflection. So on an OTDR trace, when you look at an OTDR trace, what you're going to see typically is, anywhere there's a spike, it's usually a connector, but it means there's reflection. So on an OTDR trace, an APC connector will look something like that, where a UPC connector will look something like that. An APC connector will have a much smaller reflection peak because it does have less reflection. And so to kind of tie this all in, I'm going to switch over to my OTDR here. And so I have an OTDR here. In fact, let me put this fiber down so it doesn't get in the way. So essentially the OTDR that I have here, and let me get a little fancy on you, is our FTB1. So I essentially have an FTB1 here. So this is my FTB1. This one has two modules in there. One's a 1310, 1550 standard dark fiber tester. The other one's Dwdm. So they're essentially the same. And so this is the test set that I'll be doing a bulk of the training on. And so I'm logged into it right now via VNC. And I'm just going to do a quick trace. I'll set it for 30 nanoseconds, and we'll come back to what I'm doing here, as far as setting it up, because that's part of the first time right stuff. And I'm just going to do a quick trace, and I'll start it at 1550, and we'll start getting results here. And so this is where, understanding a little bit of the fiber theory ties into the analysis of the OTDR trace. And so we're going to start looking at some of this data and putting some of this information together. And so once it flattens out like it has right now, so if you notice here, it's kind of flattened out. Once it's pretty flat like this, I can stop my trace. So here's what we're looking at as far as this OTDR trace here. So let me turn off my marker here. So essentially what we have these different reflections here. And so we have these different reflections on these different locations here. Anywhere where you see a spike, like right here, this is essentially reflection. And so the different types of events we're looking at, and you'll kind of see them down here, these different symbols. This symbol right here, event number 10, that I'm looking at down here at the bottom, this essentially is reflection because it goes up and it has some loss. So it comes down below the starting point and it comes back in. This is typically a connector. This means this event has loss and it has reflection. And then below that, event number 11 here, we don't see reflection, but we do see loss. This is what we call a non-reflective event, typically a splice, could be a pinch. Essentially what this means is there's no reflection here or no detectable reflection that we care about. And so these are the two symbols that we're looking at. So if you were to look at this and kind of overlay it and zoom into this connection here. So if I were to select this event here, 6, and then over here to the right, I have this this nice zoom in button over here to the right. It's kind of hard to see. I'll click on that. And so if I were to zoom out and talk about, so from a higher level overview, we have here basically this is boss. Anytime you see a spike, that's reflection, right? And of course, you can also have gainers. So you can actually go up a little bit and then back down. And so, there are different ways to, to interpret the OTDR trace. I mean, different types of events to interpret. So it's important to look at those very, very closely. And so in this situation, that's what we have here, right? So if I go back to my OTDR tab, these are the settings that I use. And, distance down here. And so that's what we see there. And so this is what we're talking about. And somebody mentioned that I said higher reflection for APC. What I meant to say was lower reflection. And so with Apc connectors, you have the neg 60 dB or better. And so obviously it's a negative value, so it's a reverse. Sometimes I'll say higher because I'm thinking higher number. So you have to apologize for that. But certainly into the settings here, we have the range, and I have the range set for 10 kilometers. And what I want for an OTDR trace is I want to, which is what we see here, and I want to see the noise floor. It's really important for me to see my noise floor clearly and to see the end of fiber. And so in this case, I do. In fact, I might be able to get away with 5 kilometers here, which would push this out. In fact, I'll set it for 5 kilometers. So when I retest, it'll fill up the rest. Pulse width and duration work hand in hand. Pulse width is the length of the actual pulse itself, and we measure it by default in time. So 5 nanoseconds, 30 nanoseconds. That's how long the pulse is in time. So the laser turns on for 5 nanoseconds and turns off. It's about a half a meter pulse, right? So about a foot. That's also our sampling. So we're looking at the fiber, with very fine granularity of resolution. But the problem with these shorter pulse widths is that you can't test as far. So with 3 nanoseconds, I could essentially, test, it would launch, down here somewhere on the scale, but would quickly get into the noise sooner. But I do get good resolution. So spatial resolution, right? What I can see. And events, how close events can be together. And I'll show that in some examples. But my pulse width down here, they up here somewhere, testing. And this is, would look something like this. I could see the entire fiber, but look at all of this loss resolution. So one of the first things that I look at when a customer sends me a trace, I look to see how high up in the scale it launches and how much noise there is. If I see a trace where, it's launching way up here at 30 dB, I don't like that. Sure, you'll use 1 microsecond, 2.5 microsecond pulse width, but, as long as the long, then that's not a problem, right? But if you were to shoot at that pulse width and the span ended here, then this is all lost power. This area here is all lost power. I want to be able to see the end of fiber and the noise, but I don't want this much margin between the two. Usually I like between just above 5 dB above the noise floor. And our noise floor typically is around 5 dB. So I want to be above that. And I want to have a nice clean trace. So when we're looking at pulse width and duration, so an OTDR sends out a pulse of light, right? It sends out a pulse of light and it just interprets the backscatter. The longer the pulse, the further you could test, but the less spatial resolution you have. And what spatial resolution is, how can I detect 2 events that are close to each other, right? How can I detect two events that are close to each other? And so in this case here, if I were to zoom in to one of these traces, we can kind of see what we're looking at. So if I zoom into trace, so this is event number 4, rather. There are 2 connectors here. What I did was I plugged in I plugged in a bend insensitive jumper into the middle of my span, just to show close events and to show what Todd's asking here about gainers, right? And so what I have here essentially is I have G.652 standard glass here, and I have G.652 standard glass here. And in between them, I have B3 bend insensitive jumper. It's about 30 feet long. But if you look here, we're only measuring one event because we could see that there's 2 reflection peaks here, right? We can see 2 reflection peaks, but we're not getting down into the noise floor. And so when I'm trying to do troubleshooting or first time right testing, I want to make sure that I can see as much as I can while I'm there. And so in this case here, we can't separate these 2. If I look at the event table for event number 4, we see that there's a merge. If this was a splice, we wouldn't be able to see the 2, right? And it's at 328 meters, and it has 0.3 dB of loss and minus 56 dB of reflection. And so this is what it's telling us for this merged event, but this is not necessarily a merged event, right? I mean, it's a merged event, but we're not separating it. And so here's what's happening here. I shot this trace at 30 nanoseconds. At 30 nanoseconds, and retest this. So I'm going to retest this at 5 nanoseconds. We're going to start to see some separation between the events. A little bit of extra noise. Stacy. And so this is what happens when you reduce the pulse width. As you increase pulse width, you can drop duration. So it's kind of like hot and cold water type of a situation. You got to find that sweet spot. So 2 splices 100 feet apart with a short pulse width. I can't test very far. What I can do is I can start to clean up the noise with duration. And I'll talk about that here in a second. So I dropped this down to 5 nanoseconds and retested here, right? So I've dropped it down to 5 nanoseconds and retested. I can zoom back into event number 4 here. And now we see 2 events. We have a 4 and a 5. So we have 2 events now because as I drop down to 5 nanoseconds, it reduced my dead zone and it improved my spatial resolution. And so the key here is, honestly, the key to all 3 of these knobs is to get them as low as you can and get a nice clean trace, right? Within a reasonable amount of time. And so now if I look at this, I can separate these 2 events. If I go to the event table, event number 4 is a gainer. And somebody asked about what could be causing a gainer. The most common issue with gainers is a change in mode field diameter, right? So change in mode field diameter, which is what I have here. Again, I'm going from standard fiber to bend insensitive fiber back to standard fiber. And so what happens here is as the OTDR pulse is transitioning to the different fiber type, the way the backscatter is interpreted is confusing to it. And so it looks like it's gaining a little bit of power. So we get a negative value here. So you get a negative loss at this location. And on the other side, we have something called a loser, which is an exaggerated loss on this side here. The only way to really accurately measure an issue like this, gainers and losers, is to test bidirectionally. So it is incredibly important to test bidirectionally to get your average. We're seeing a lot of mode field diameters issues in the field today, particularly because we're seeing these pre-terminated FTPs inside the sites. And within these offices, those pre-terminated FTPs might be using bend insensitive glass, like an A1 glass or something. And they'll run that tail out to the feeder fiber and splice to the OSP cable, and that's standard glass. So we're seeing a lot of that example there. So it is important to test bidirectionally, because when you look at this trace bidirectionally, this way we have a gain in power, this way we have a loser in power, right? Looking at it from the inverse direction, we're going to have a gain in power this way, and we're going to have a loss in power this way. And so we need to average out, you know, this gainer to this loser and this loser to this gainer, right? And so in this example here, it's a neg 0.170 is my gainer, and my loser, whoops, let me zoom back out here, and my loser is 0.466. If I were to measure this bidirectionally, it's probably going to be a really good connector, right? And so the only way I saw this was I reduced my pulse width. If I set my pulse width too high, say 100 nanoseconds, and sometimes this is unavoidable. If you're testing a long span, you have to use a long pulse width. There's no way around it, right? So that's why sometimes you do a short shot and a long shot. You do a short shot at, say, 10 nanoseconds or 5 nanoseconds to see everything within the office or close to the office. A lot of transport vendors want a short shot because the way their equipment works with their auto equalization and auto optimization, they have this fancy troubleshooting tools that they use. It really cares about any front end loss close to the amplifier. So they use a short shot to see everything within the office and everything close by outside. Then they use a long shot to test the entire span. Yeah, we have an application called IOLM that gets around that by shooting a short, intermediate, you know, long, ultra long haul shot all in one shot. But with OTDRs, if you set something at 5 nanoseconds, that's all you're seeing as a 5 nanosecond perspective. If you set it at 100 nanoseconds, that's all you're seeing. It's almost like focusing on a room full of people. You focus on the back person in the back row, the person in the front is not as clear, right? And the inverse is true. So if I increase the pulse width up to 100 nanoseconds and I retest this, we're going to start seeing, you know, some different views here. So I'm going to look at that same connector where we have that gainer and loser to kind of show you what we're looking at. And you're also seeing this one event here. If you noticed it before, the peak is getting taller. As this peak gets taller, this is worse reflection. So this is worse reflection, right? I can go ahead and stop this because it's nice and flat already. And so I'm going to zoom back into event number 4. And this is event number 4. Now we only just see one. In a maintenance situation, this is incredibly valuable to understand because let's say that you get a call from your knock center, or let's say you're doing a maintenance issue. Your customer calls you and says, hey, that fiber you handed over to me, we're getting higher reflection, go out and fix it. And so you go over to this location in the office because you ran the tie cable and you're looking at this location, and right here, you know, we have a connector. And so looking at this, let's say the value is really, really high, right? Let's say that you have really high reflection here, incredibly high reflection with some loss attached to it. So it looks more like this, right? You're going to say, hey, you know, I have a neg 30 dB reflection here, which is bad reflection. This is high reflection in an amplified system in particular. This can cause a lot of issues. And so you have this high reflection. And so, you know, what does this mean for us in regard? This neg 30 dB, you're going to say, you know what? Here's the connector. It's at, 2,000 feet. So you go to 2,000 feet and clean this connector, not fully realizing or remembering that there's another connector, that sits right over here. This connector is the one contributing the reflection. This one's fine. This one's neg 50. It's great. This one is closer to neg 30, right? And so you're at the wrong place cleaning the wrong fiber. And so this is part of the limitations to the OTDR and how to compensate for that. And this is one of the ways that you can compensate for the OTDR is by reducing the pulse width and taking another look at it. And so that's how these two tie together. And to pull in duration here, if I were to set this trace at 3 nanoseconds for 5 seconds, very short pulse width, I can see events time. Our OTDR has a 4 hertz analyzer, meaning 4 times a second. At 3 nanoseconds looks like this all the time. And it's just noise. The software 4 times a second looks for movement, looks for noise, and flattens it out every time it sees something moving. So if you increase your averaging time, you can improve the noise profile. And so if I were to be short for this span, I want to say this is just under 5 kilometers. You'll see that it will clean up a little bit more as time goes on. You can watch over here to the tail end, and it starts to get, the noise starts to get smaller and smaller and smaller. But if the time is still ticking and this noise is not moving, then you have to increase your pulse width or improve your launch conditions. In this case here, 3 nanoseconds, there's too much noise there at the end. I need to figure out a way to clean that up. And so it's starting to clean up a little bit. I am getting some good information on the front end. If I go to event number 2 here, the end of my launch cable, you know, I can see my launch cable here. So this is the patch panel. And then I can see something here that's 20 meters away. So I'm getting really good spatial resolution. It is important to use a launch cable because this is what pushes out the dead zone. And so launch cables have different names. Launch cables, pulse suppression, kind of does all of that, you know. After every single reflection in a fiber, we're going to have something called dead zone. That's a portion of the fiber that the OTDR is blind to. It's essentially seeing its own light reflected back and blinding itself. It's kind of like looking into high beams, right? And so this is why it's important to understand the theory of fiber, because at 3 nanoseconds, if I were to hit this measure button, our dead zone is roughly, let's change the settings here. I got it set for meters. We'll change this over to America here. For those of us here in the US. And so my dead zone's roughly 9.2 feet here, right? So after 9.2 feet, I can start seeing again. This is at 3 nanoseconds. It's incredibly good dead zone. But if I increase this up to 100 nanoseconds and retest it, we're gonna start losing some events inside of that dead zone. And so I'm gonna go ahead and stop it because it's flat. And then we'll zoom into this event here. And I'm still seeing that one event, so that's good. Let me zoom into it. But you'll see how the dead zone starts to bleed into it, right? And so at 3 nanoseconds, you know, we were seeing something like this here, right? We're seeing this, and then we're seeing this. You know, so we had this, we're down into the noise floor, it looked a lot better. At 100 nanoseconds, it looks like this. And if I were to go up to a higher setting, like 500 nanoseconds, which is incredibly high power, for this kind of a span, then we're going to see even more issues. And so, so this is using 500 nanoseconds. If you start to see this flatness here, and this much loss of, you know, this much wasted power, this is a trace that I would turn back. So as a tester, when I'm standing in front of the machine, I want this end location here. I want this end location here. Somewhere closer to roughly around here, right? Here's my noise floor. I want to be above the noise floor. I want to have a nice clean trace. This is all wasted power. This test could go on and on and on for quite some ways. I'm oversaturating the receiver, so my peaks are starting to flatten out. But if you notice, they're getting wider and wider. And so remember, we had 10 feet of dead zone. If I set my markers, over 300 feet of, almost 300 feet of dead zone. What that means to me is that anything within this 300 feet here, anything within this 300 feet is this value here. So I'm showing 0.6 basically. My reflection's good, but my loss is high, right? It's a little high. This is actually 2 events and 300 feet of fiber. And so this is what we start to happen. And so this is what I look for. And I want to make sure that I don't have this issue. I don't have this issue. That's one of the first things that I look at is, you know, as I mentioned before, is the look of the trace itself. And then I drill down into the readings. If you look over here at event number 5, and if I go to the event table here, this is, it has 0.1 dB of loss, 0.133 dB of loss, and minus 41 dB of reflection. So this is a fail for me in this particular situation. So I need to improve it. And it's probably this dirty connector here. So I'm going to reach down and just use a quick cleaning method here. In fact, I'll just probably just use a little clay top, but I prefer like a wet to dry solution myself when I'm cleaning. But let me clean this fiber up and see if we can improve the performance. And this is really important to understand because probably most of the callbacks that I experience, or most of the traces that I look at that require callback, or retesting, is honestly the connector at the FDP, the connector at the end of the launch cable. It's by and large, one of the worst. And so I'm going to go ahead and retest this. I'll drop this back down to say 10 nanoseconds, something more reasonable. And we'll retest this and we'll look at that event again. It won't be event number 5 because we should have some additional events here. So you see it's right there. So the peak is not near as tall, At the same time, with 500 nanoseconds, we have more issues with reflection because we're throwing more power at it. It's still a percentage of light coming back, right? But it's more total power hitting the connector. So if I take a garden hose and just slowly crack out and hold it up against the wall, it'll run down that wall, right? It'll just hit the wall and run down the wall, not a big deal. If I increase the pressure of the water, it's going to splash off of the wall into my face. That is reflection. So as you increase power, you're going to have more issues with reflection, especially up close. And so in this situation here, we'll look at this connector that I just cleaned really quickly. And now we're neg 57, which is much better, right? So now we're neg 57. The loss didn't improve much. So you can have good power, good loss, but bad reflection, right? Any of us who've ever done troubleshooting on the operation side, you get a call from the NOC, Network Operations Center, saying, hey, Kevin, you're taking errors, bit errors on that one system. I take my power meter, I plug it into the receive side, and I have good power. Then I start cleaning fibers. Why am I cleaning fibers? I'm cleaning fibers because of reflection, not because of power. I have good power for the system. I don't have good reflection, right? You can have good water pressure, but that doesn't mean that the water tastes good, right? So those are two different things in this situation. And so understanding how to set up an OTDR is critically important in how pulse width and duration work. So again, pulse width, is the length of the pulse, it's your sampling, it's how far you is what clear. They don't move much at all because they're real. Noise will bounce up and down. And so the longer you let your trace average, the better your noise. And so OTDRs do have how far you could test. This one that come in different varieties of models, right? You have an entry level, kind of last mile OTDR, and then you have ultra long haul stuff and everything in between, depending on your application. Specialized OTDRs like Dwdm, all of those things, all of this is relevant, whether it's a short reach OTDR or an ultra long haul OTDR. It's range, pulse width, and duration. The difference is some can test further than others, and some have additional wavelengths that you don't typically see. Another thing that's important to do is to test multiple pulse widths, so a short wavelength and a long wavelength. So in this example here, I'll turn on 1310 and 1550, and I'll do a quick test at 30 nanoseconds here, and then we'll compare the information. So I'm going to grab a piece of fiber here. I'm going to pinch it here in a second. So, whoops, I set the time too long. We don't need to sit here and watch this thing test for that long. So let me do 5 seconds each. I'll do a quick test here. And then let it test. And so we're going to look at that one event or that one connector that I just cleaned. So I'm going to run a quick test to get like the baseline here of a fiber with no pinches. So I'm going to stop this. So event number 6 here at 1550 is 0.123. That's easy to remember. Go to next fiber, and it is 1310. It is 0.09. So it's actually a little bit better. But in an ideal, not an ideal world, but in a typical situation, 1310 has higher attenuation. So if you look at attenuation wise, 1550 has about 0.2 dB of loss per kilometer, roughly, right? Depending on the fiber type. There's ultra low loss fibers and whatnot, but we'll just talk about, just generic information. And about 0.3 dB at 1310. And so span wise, if I had a 100 kilometer span, roughly 60 miles, 20 dB at 1550, 30 dB at 1310. Tremendous amount of difference. Every 3 dB we double, so that's a huge difference. This is not only true for spans, but connectors and splices. So 1310 is typically higher attenuation or higher loss. And in this case, what I'm going to do is I'm going to pinch the fiber. I'm going to do something here to make the OTDR look at something that it doesn't want. So this part right here, you don't normally do. And so I'm going to go in here, pinch this fiber, and I'm going to retest it at both of those wavelengths at that location number 6 there. So we'll let it run and do its thing. So there's 1550. You know, I didn't pinch it enough here. Let me retest that. Let me stop that and retest it. I'll do a better pinch here. Of course, when I don't want to pinch a fiber, I pinch it. When I want to pinch a fiber, it doesn't work out my way. And so we'll roughly do that real quick, and then we'll kind of finish up here. And so here's 1550, right? So we're pinched pretty good, and then here's 1310. And so looking at 1550 here, we have 8.4 dB loss. So we went from 0.123 to 8.4. This is service affecting easily, right? Easily service affecting. If I go to next trace here, we see 1310 is 3.7. So it went up about 3 dB, which is fairly high, but this is a pretty significant pinch. What's happening here is I'm applying pressure or compressing the fiber, exceeding the band radius, and the larger wavelengths will react harshly to changes in the size of the core because they're physically larger, right? So if you have a pinch in the fiber, this is what it looks like. And it is very common to have 1550 fail miserably and 1310 pass, right? So this is another issue that we run into where there's a pinch in the fiber, and it's usually at the launch cable, or it's in a splice tray. And those things are easy to fix while you're standing in front of it, right? If you have a dirty launch connector, if you have a pinch in the fiber and you're looking at the results and you see this big drop, and you see that 1550 significantly worse than 1310, this is a pinch. You need to identify that pinch and fix it while you're on site, right? While you're on site. And so to kind of summarize some of this here, of some of the stuff that I talked about, when it comes to an OTDR, it's important to understand the critical parameters and the pass-fail thresholds of all the different components you're looking at. What is my splice loss? What's the difference between my unidirectional splice loss and my bidirectional splice loss? Unidirectional splice loss, I'm only looking at it from, I want to see a gainer and a loser from one direction. So that's an inaccurate measurement. The best way to measure a splice or a connector is bidirectionally, ideally with a short and a long pulse width. That way you can look for fiber management issues in the cable. It's rare to have, so back when I was working in fiber, there was more manufacturing and cabling issues. We're seeing much less of that occurrence. We know with the quality of the manufacturing that we have today, but we are still seeing a lot of cable placement issues, a lot of environmental issues that contribute to some of these problems. And so it's still very important to troubleshoot this kind of stuff, right? So it's important to understand that you need to look at these bidirectionally, ideally with two wavelengths. We're starting to see a shift with some customers just doing a single wavelength 1550. And when I was testing on the railroad right away, we had very short time, to be able to test. And so it was important for us to be able to do it quickly. And so we tested only at 1550. And if we had a failed splice, or if we had a failed event at 1550, we'd shoot at 1310 to make sure it wasn't a pinch. We're starting to see a shift towards 1625 as well, particularly for hyperscale customers. Your big single data center customers like an Amazon or a Google that are starting to require 1625. We're seeing it with ultra long haul, of course. And of course, now we're seeing a lot of DWDM stuff. So DWDM is being pushed further and further into the access side. So now contractors that were typically just running drops or wiring radios are now dealing with fibers that carry higher capacity. That was typically relegated to the long distance world. So we're seeing a big shift in that technology where your 1310, 1550 OTDR is not sufficient. So now you're starting to look at some of these more specialized OTDRs like DWDM. So these types of things are very ripe for rental as well. But the good news is they all kind of set up the same as this, right? And so understanding what reflection is, what's good and bad. Typically, we see pass fail between neg 40 and neg 50 dB for reflection. The higher the value, if you disregard the negative, the higher the number, the better. So you want 50s and 60s, right? Those are good values for reflection. And understanding the difference between APC and UPC connectors. And when looking at pulse width and duration, you want these two numbers. I want pulse width as low as I can get it within a reasonable amount of time. If you're working with specific customers, they may specify a duration. They may say 60 seconds a wavelength, 30 seconds a wavelength. In that case, you set the duration for 30 seconds, and duration and range are pretty much no-brainers. You're only tweaking pulse width. And when it comes to pulse width, just drop it down as low as it'll go and still clean up at the end of the duration. And that's really what you do with an OTDR. And then inspect and clean, like it's the most important thing in the world, because it literally is for a lot of this testing. If I look at a trace and I see it launch with a ski slope, or after a reflection, I see a ski slope, this is bad. This tells me there's high reflection and there's probably high attenuation, right? I don't want to launch too high and drop off too quickly. I want it to be down here, but not so low that it's noisy at the end. And so you got to find that sweet spot somewhere between here. And again, I like to be somewhere between, above 5 dB, just above 5 dB of the noise floor, right? That's on our OTDR. Some other OTDRs might have a higher noise floor profile. It really depends on which product you have out there, right? And then after that, it's just basically just saving the results and going to the next fiber, and a lot of information in a short period of time here. But I really wanted to just kind of get, across some of the biggest things that we see in ensuring the first time right testing. A lot of us out there, or at least I used to be, one of those people that worked for a living, doing splices, right? You're out there splicing the cable, doing all that hard work, all that engineering, all that pulling and placing fibers and splicing fibers. The last step that you need to take before anything gets invoiced, before customers get turned up, is your closeout or delivery package, right? And what is required of that? Good test results. And having good test results and understanding what can cause issues. Dirty connectors are probably the biggest issue with failed tests that I see today. If it's a bad splice, it's a bad splice. You know how to fix that. But if it's a pinch, you know how to troubleshoot that now and compare the short and the long wavelength. If you shoot too much pulse width, you're going to start masking events and be in the wrong place or troubleshoot the wrong thing. And so understanding all of those things from the theory side and then the fiber side is critically important. And so with that, I will hand it back over and take a look at the questions and answer any questions that you might have.
Thanks, Kevin. Again, wonderful presentation, as always, nicely done. As Kevin mentioned in his presentation, this EXFO equipment is available for rent. We do have the ability to rental equipment and you're an issue with it. And if one of those is today, we do have exchange services with our full service rentals. We can support you for long term, and you can use different types of budgets, whether it's capital budgets or operating budgets. We have a lot of programs to help you save money and again, get quality, accurate information and equipment overnight. So please feel free to give us a call at any time. You'll talk to a live person and we'd be happy to be of service and help you. Thank you. With that, we'd like to open up for any questions.
Yeah, there were a few questions that I've answered during the session. So there's about 17 questions asked there. So I think I covered most of them. I'm starting to answer some now. So.
Okay.
Let me see what we have. Oh, there we go. There's a bunch coming in now. The auto feature on the OTDR, we need to be careful with the auto feature. And I probably should answer from the top down rather than the bottom up instead of top down. Auto mode on OTDR, you have to be careful of, particularly Dwdm network. Auto mode's great. In fact, I start with auto mode typically when I'm testing. So I'll get into the OTDR, I'll set it up for auto, and I'll let the OTDR narrow down. And we auto to the duration. So auto is much better than it used to be, but be careful because auto will send high energy out initially, like a big pulse to analyze the span. And it is powerful enough to damage transceivers or SFPs, especially Dwdm SFPs if they're close enough to you. So be careful with auto mode. It's a nice way to start, but it's not a nice way to, you don't want to stay there. And so let me look here because there's a ton of questions here. So let me start from the top. Calibration of an OTDR. We do recommend annually. and I got to be careful with this answer. A lot of our customers calibrate first, typically when the connectors go bad. So the connectors on the OTDR, you really got to inspect and clean those. Some will calibrate annually because it's required by the municipality or the governmental agency they're working with. Others do it just as part of good practice. But it's recommended for a year officially on paper. But if your results are looking good, there's ways to look at your OTDR. The most important thing is your launch. So if you shoot an OTDR trace, look at your launch reflection if you can measure it. Our newer OTDRs, we can measure our reflection a lot better. You want to be above minus 45 dB for your launch, not at the FTP, not the end of the launch cable, but the actual OTDR port. Neg 45 dB or better. So neg 50s, neg 60s is what we want. Somebody asked if a receive cable is recommended. It's always nice to have a receive cable. It helps with verifying continuity and looking at the far end. Right now, most organizations don't do bidirectional analysis on the launch on the end of the FTP at the FTP because they only look at it from one direction, right? You only look at it from the launch fiber side. So a tail cable is not necessary, but it is nice to have. Is it necessary to test 60 seconds per wavelength? It depends on the length of the span and the quality of the trace. We do see the longer 60 seconds when we get into ultra long haul more often. That way you're trying to get away from using too long of a pulse width. So to get away with a shorter pulse width, increasing your averaging time is ideal. 60 seconds is not uncommon to see in an ultra long haul network. We do see it in some short haul stuff. And that's it's a debatable discussion, but once your trace flattens out, the rest of the time on there is wasted. So if you're shooting 3 nanoseconds or 5 nanoseconds and 30 seconds in, it's flat, you're not getting much benefit out of that, the remaining time. And so somebody says, for some reason our duration button is frozen, we cannot move it. That's because you don't have the OTDR option. You probably have IOLM and you're in real time, or you're locked into real time only. Contact us at support@exfo.com or get a hold of your representative with TRS or EXFO. And somebody said, should you always have an end of fiber at 25 dB? And so I don't know if they mean end of fiber detection threshold. You don't want to increase that end of fiber detection threshold above the default unless you're testing through something like a splitter that has high loss. Is IOLM just as accurate as an OTDR trace? I would say IOLM gathers more information. So it's using OTDR-like technology. So IOLM is our advanced OTDR tool. And so what it does is it gathers more information. So instead of taking one trace at one pulse width, it might take 10 shots at 10 pulse widths. And then it'll create a composite and it has advanced analysis behind it. So it does gather more information. It gives you more information for sure. Apc connectors are really good. So somebody mentioned your Apc connectors are good. I talked about how APCs have less reflection, right? Although I said higher reflection earlier, they have less reflection because of that 8-degree angle. It's not uncommon for APC connectors to flag as splices because the reflection is so low that the OTDR ignores it. Most OTDRs ignore reflection that are better than minus 72 dB or minus 73 dB. So there's reflection. It's just so good we don't mark it as a splice to prevent us from picking up on noise. I say most folks should use APC connectors if you can get away with it. Somebody's asking, should I use UPC? Should they use APC or UPC? If I was building a brand new network, I like APCs. Less reflection, probably less, issues with noise. But most systems today are still UPC. All of our optical equipment now by standard, standard package delivers with APC to give us better performance on our unit. What are my thoughts on the OX1 for troubleshooting? So the OX1 is an EXFO product. I do love the OX1. It's certainly not a direct replacement for an OTDR because it doesn't have the sensitivity. It's really designed for kind of prem technician, the technician close to the house, troubleshooting. But it will look at events for you. And more importantly, it'll give you loss and ORL, which are two critical parameters that a standard power meter will not give you. So an OX1 is kind of our small troubleshooting tool. how do I make my OTDR identify DWDM instead of a high reflection event? So what they're talking about is if you're using a DWDM OTDR testing through a DWDM MUX, you're going to get some sort of reflection, and there can be higher attenuation from that MUX. But the OTDR is going to say, hey, this is high reflection, because the OTDR doesn't know that it's not a high reflection. It doesn't know that there's a DWDM coupler there. You're better off with IOLM, which is our advanced OTDR suite. You can create custom events and tell IOLM to expect to see a MUX. And if it expects to see a MUX or a splitter, it'll look for that profile of a MUX and say, this is a MUX. And then in small print below it, it might say something like, or a really bad connector. Right? And so, that's probably the best way to do it. And so let's see here. Can I do this with IOLM? So I've done this presentation with IOLM, so that's certainly something that we can do. Let's see here. What causes the ski slope on the launch? When I talk about the ski slope, typically a bad connector. High reflection is the most common issue for that. If you're constantly getting a ski slope at the launch, it's going to have to come back for calibration, right? It's going to have to come back for calibration. And as Scott mentioned, they do have a calibration lab there at TRS. So that would be a good option for you. How to identify a macro bend? I talked about that. 1550 is going to be worse than 1310. We do have macro bend detection on the OTDR as an option. So you can put that in there and it'll just kind of look at it and flag it for you.
And Kevin, on the calibration, all rentals come freshly caled so that for the duration of the time that you're planning to have it, it will be calibrated. And if you should keep the equipment past that, we work out a swap out, an exchange service for the rental. So we take care of all the calibration as part of our calibration service.
Excellent, excellent. So that is a great service for sure. Somebody's asking that they say, hey, I have a customer who plugs UPC into APC. This is very bad. You can damage the connector. One is flat, one is angled. In the past, you could plug a UPC into a PC into an SPC because they were all flat cleaved. The performance wasn't always great, but they were flat cleaved. APC into a UPC is an angled cleave, and you'll see about 3 dB of loss in that range and high reflection. And you can damage a connector. It's not advisable. I've seen it too many times, and it will cause issues with your system. Some of these are going to, I'll have to respond back with an email because there's some long answers here. I have a single mode live port and use 1625 wavelength, and you get a live fiber detected message. If you're getting a live fiber detected method, so basically we have an in-service option for our OTDR where you can shoot while there's active light on the fiber. This particular one is 1625. I usually recommend 1650 if you can get a hold of we have a 1650 version. You get yourself further out of band. If it says you're detecting light, either you have really high reflection or there's light bleeding over, just enough light bleeding over. So if you get a power meter, see if there's any light on the fiber at all, any transient light that might be bleeding over into that port, which can happen, right? It also depends on how they're, outfitting their channels. So I don't know how high up into the L band they're getting. And so there will be a recording, I assume, for this. And is an average loss a patch cord can cause while carrying out a trace. So a patch cord, if it's just a short patch cord, we expect half a dB or better. And most of the attenuation is coming from the actual connection itself. And so it should not attribute a lot of loss. But it's advisable to use a launch cable and not a patch cable. And the length of that launch cable will vary depending on the span that you're testing. One good way to find out is to shoot a trace. And as I showed you with the measurement, go to your launch on your OTDR and then set your, zoom into it and set the markers to see how long that dead zone is. So right at the launch of the OTDR, you'll see it spike up a little bit and then flatten out. Where it flattens out is where it's starting to take measurements again. The pulse is suppressed or relaxed at that point. And as long as you can see your FDP and you've given the pulse a little bit of time to recover, then that's sufficient launch cable. We're seeing most customers just spec 2 sizes. So under 20 kilometers, they might say 150 meters or 100 meters for everything under 20 kilometers. For everything over 20 kilometers, give me 1,000 meters, just for simplification purposes there. But a launch cable is essentially a long piece of, it's a long jumper that allows you to see your FDP. So to upgrade, if you only have a dark fiber version of the OTDR, to upgrade, unfortunately, is a hardware thing. So you'd have to get an in-service version of the OTDR. Can we adjust the VFL output? So the visual fault locator output? No, we cannot. It's just it's set for the power level that it's spec'd for, and so it's not something you can adjust. Be careful with VFLs. I do this series on damaging SFPs and high energy output VFLs. These ones that test tens of kilometers that you can buy off of the internet can damage transceivers. Those are dangerous optics, so be careful with those things. Can you damage a 1550 optic with a 1625? We're starting to see damages with Dwdm in particular. Theoretically, it can happen. With the older systems, we didn't see it as often. Like the older 1310, 1550 optics was fairly rare. But with Dwdm transceivers, they're much more sensitive to the energy. So those you got to be careful with. What causes a fusion splice to show a reflective event? When I was splicing, it was typically the fiber breaking, but the heat shrink holding it together. So there's a change of material type there. Could be an air gap, could be an air bubble causing reflection. You should not see detectable reflection in a splice because you're melting it together and there should not be that air gap. Can you damage optics while shooting OTDR hot? Yes. So I talked about that before. I do have a series, and maybe that's a link that we can share where I talk about how high energy OTDRs can damage optics. With IOLM, we actually have something called Sfp Safe Mode that allows, so it's a configuration that you load that is kind of opposite of auto. It starts with shorter pulse widths and increments up until it sees the end, then it stops. So it doesn't use higher power or higher energy than it needs to. How much dBm can cause a burnt fiber tip? I have some great videos that I could show you, and maybe I'll give you some links to that, where Raman amplification is causing issues. And so, you know, I've seen burnt fiber, particularly with analog RF video systems. When I used to work on analog RF video systems, you know, we'd see plus 20, plus 22 dBm coming out of the head end because they're cascading EDFAs or amplifiers. I've seen videos and a lot of pictures and images from my customers with Raman amplification because of high reflection or pinches in the fibers being burned. So it is a real thing. And so that's one reason why it's important to analyze your OTDR traces. And I'll leave with this question here. So it's very important to analyze your OTDR traces because of issues like that, right? You don't want to leave those high reflection connectors in there. You don't want to leave those pinches in there. It's going to affect the transmission system if it's turned up without somebody validating that data. So it is important to understand what causes those issues, how it can impact your system, and how to fix it. And so with that, I'll close it out because we've gone over a little bit. I know I can probably answer questions here all day. I enjoy it quite a bit. But we do definitely, well, I want to thank you for your time, and I hope you found this valuable. And certainly look forward to doing more of these in the future. Thank you.